Hello, everybody. Today I'll be doing electric and gravitational fields for physics. And let's get started. This is mainly for A-level physics, 9702. So I'm going to begin with gravitational fields. So the definition of a gravitational field is a region of space where a body having mass experiences a force. Gravitational fields are usually radial. However, at small distances, they can be assumed to be uniform. This is when distances are approximately equal to the radius of the mass. Direction of the field lines showcase the force due to gravity, and the spacing between individual field lines indicates strength of the gravitational field. Law of gravitation. Any 2-point masses attract each other with a force that is directly proportional to the product of their masses and is inversely proportional to the square of their separation. It follows this equation over here, F equals to negative G m1 times m2 over r squared, where r represents the separation, and since it's inversely proportional to the square of the separation, it's r squared. M1 refers to a mass, and m2 refers to another mass. The negative sign in front of this represents that the force is always attractive. Two masses will always attract each other in a gravitational field. They will never repel. G, which is a universal gravitational constant, has a value of 6.67 times 10 raised to the power of negative 11. This will be given in your data booklet, so there's no need to memorize it. Gravitational field strength, its definition is the force exerted per unit mass at that point. And take note that this is a vector. So G equals to F over M, and using the formula that we discussed by the law of gravitation, we substitute that as F divided by M2, and then we get negative G M1 over R squared. M1 usually refers to the mass of the larger body. And if you're asked to draw the graph in your examinations, you can draw it as such. And since we know it's inversely proportional to R squared, it'll be a curve, that an exponential curve, which will never cut the x-axis. So remember, while drawing the curves, do not cut the x-axis. And for your y values, if you're given a value called x or any value, remember that at 2r, or distance from the center is twice the radius, you get 0.25, will decrease by a factor of 4. And when the distance is 4r, where r represents the radius, it'll be 1/16 the value at the surface of the mass. Definition of gravitational potential energy is that the work done per unit mass in bringing a mass from infinity to that point, and is denoted by the Greek letter phi. mgh doesn't really apply here when you're finding gravitational potential energy, because this formula assumes that G is constant. And that's not the case. We just saw that G variates or changes with R squared. And hence, this only applies for short distances. And it will be usually given in the question if they want you to use mgh. If not, you'll have to use this formula, which is work done over mass. And we know work done can be split into force times distance. Using the law of gravitation equation, we can get negative G m1 times m2 over R squared multiplied by R, which is distance, divided by m2. Sorry, this is a typo. Which will give you negative G m1 over R. And m1 usually refers to the larger mass. And this is a graph that you will have to draw. Phi is usually joules per kilogram, and the x-axis is distance in meters. This graph is not very accurate because this graph suggests that it will cut the x-axis, but this graph will never really reach the x-axis. It will continue to go closer and closer, but it will never meet the x-axis. And at infinity, it is known that the gravitational potential energy is equal to 0. All right, geostationary satellites. These satellites orbit a planet. They can be man-made or natural, like the moon. Geostationary satellites are unique. They seem to remain in one place while you look at it from Earth. That's because their period of revolution is 24 hours, same as Earth. They move from west to east, or they rotate from west to east, and they have equatorial orbits. Advantages of geostationary satellites are that they're ideal for broadcasting and transmission of signals. and they provide a 24-hour view of one place. Disadvantages is that the transmission has a poor signal at polar regions. Because they have equatorial orbits, the distance to the polar region is very high, hence the signal will deteriorate. The signal would be weak, like I said, as the orbit is large. That I would recommend you to remember the poor signal at polar regions as a disadvantage. Circular motion and gravitational field. So a satellite that revolves around the Earth will follow circular motion, and the centripetal force will be equal to the force of attraction due to gravity. And then you equate the force equations, mv square over r, where v square over r represents acceleration for an object undergoing circular motion or uniform circular motion, and v represents the linear speed. Simplifying this equation, you get gm over r equals to v square. This shows that the mass of the satellite is not considered for the linear speed required to stay in orbit. It usually this equation shows that the linear speed required only depends on the mass of the bigger object or the mass of the sun, if you think about in our perspective. So using further equations from circular motion, where linear speed equals to 2 pi r over t, where t is period of revolution, combine the linear speed with the equation from the previous slide, this one, and you get 4 pi square over r square over period square. And then rearranging the formula, you get period square equals to 4 pi square over gm multiplied by r cube. 4 pi square over gm is a constant because mass of the Earth doesn't change, and g is a gravitational constant. Pi is a constant too. So this is actually Kepler's third law of planetary motion, and it states that the square of the period of the satellite is directly proportional to the cube of the radius of the orbit. And remember that the period has its units in seconds, and the radius has its units in meters. So if you were to use this equation to find the period of a geostationary satellite, if you find the radius of orbit of a geostationary satellite, you'll have to put 24 times 60 times 60 to make it into seconds, because it's 24-hour orbit. 24-hour period, sorry. Escape velocity. To escape the orbit, the satellite or the object orbiting has reached infinity. Like I said earlier, that at infinity, the gravitational potential energy equals to zero, and the total energy equals to 0. Hence, the kinetic energy required to escape is equal to the gravitational potential energy at that point. And you rearrange the formula to give you V escape squared equals to gm over r. This is the gm over r. All right. Next, that's all we have for for gravitational fields. I'll be going through some questions in the later videos that I'll upload. Hopefully you understood most of the stuff that I have said. If you enjoyed the content that we're putting out, please like and share this video, and comment some suggestions, and leave your suggestion in the comment section. I would love to take a look at them. Thank you and goodbye.